Hello, this is another lecture in the OCT series, or OCT tutorials, but the last couple have been focused in on coronary arteries. The relevance of plaque composition by OCT to PCI, to putting in, let's just say putting in stents. I'm me, and this is my background. It's been on other slides. If you want to read it, pause it. Why is it relevant to physicians, cardiologists, and interventionalists in particular? To some degree, we don't know because the we don't have great data, in my opinion, correlating OCT images with histopathology. At least um, it hasn't been done in a way to convey it to the interventionalist. Uh, you know, between 2000 and, or let's say 1993 and 2012, I looked at an awful lot of plaque with OCT and uh, the histologic correlations, and could tell by looking at it. And the problem is, too many people were looking for more quantitative approaches, and as physicians, and I'm going to go back into this, but as physicians, we're used to looking at qualitative data. Okay, chest X-ray. We don't look at densitometry. We look um, at the chest X-ray. We look at angiograms, um, and so we need to get back to that. But plaque-specific intervention is something for the future. When we formed Light Lab Imaging, in at least in my opinion, we were supposed to be focused on um, outcome studies for stent placement, morbidity, and mortality. And while they were being done, learn more about plaque morphology. And we now have learned some more about that, but things didn't unfold the way I would have liked. 20 years waiting for morbidity and mortality data has been painful. Better local outcomes, which I'll go into, and avoiding no reflow. And these are some of the issues which I'm going to go into individually. The final one relates to angiogenesis and failed plaque healing. Um, I'm just going to explain that with one slide at the end, but I'm not going to cover it closely in this talk. So again, there's a lack of correlation, strong hypothesis-driven correlation data between OCT images and histopathology. And like on many of the talks, our group is in part to blame. I mean, we had the facilities to do it. We had phenomenal OCT systems, our own light lab, Thor labs. We have micron scale histology matching, histopathology matching. Our own histology lab we built, hypothesis driven research. But we couldn't get coronary arteries easily. The Brigham in general used them for uh, uh, post-mortem clinical interpretations, and so they're used diagnostically, and we struggled to get them, and that really wasn't an excuse, because now we're getting them from the University of Maine and or the University of New England in Maine, and we should have done that, or so like something like that earlier. Do we know plaque composition from conventional OCT? Not as reliably as we would like, and there's a lot of problems. For one of the first problems is engineering teams were may not have been clinician heavy, and they were referring to plaque as lipid, but we're looking for necrotic core. So you'll see classification systems based on lipid plaque, but lipid plaque can be necrotic core, it can be xanthomas, it can be PIT, pathologic intimal thickening, and um, we don't know uh, necessarily. And there's still, and we'll go into, there's a struggle differentiating to some degree, really some hardcore plaques with a hard core versus a necrotic core. So if we take a plaque like this, plaques are complicated, and it's likely that you're gonna need to place the stents um, relative to the composition with the plaque. So you look at that on the left in the black box, that necrotic area. Now that necrotic area where the green arrows are um, goes up and into an area that's PIT, And there's PIT along the length of here, along with necrosis. And the red arrow to the right just shows a TCFA with no necrotic, long necrotic core. And I'll get into that point in a minute. But the point here with the slide is this, if I had my way, I would put the stent right over the top of this thing and prevent it from causing problems down the line. But you need to know what's in there. Now, the image interpretation, to a large degree for the last 20 years, people have used the diffuse border criteria, which right from the beginning we thought was not working. I mean, it was a nice postulate. I'm not critical of the group who did it, but I don't think, this slide illustrates why it doesn't work. So if we look at the plaque on the bottom first, and again, that diffuse border criteria was established with the quote lipid plaques, which whatever those are. But the plaque on the bottom has a necrotic core. Now, if we look at the area where the yellow arrow is, both in the histopathology and on the OCT image, in the histopathology it's necrotic core. Now when we go up to the OCT image where the lookup table is orange here, the border is diffuse, and so by that criteria, this would say, well, we're looking at a lipid plaque, not a hard necrotic core, that we're just losing signal. But if we go just a little bit to the right, we go down to the histopathology, it's still lipid necrotic core, but we look at the OCT image and the border is sharp, which it should be between lipid or necrotic tissue and intima. And so what's happening here is the diffuseness isn't coming from the core. The diffuseness is coming from, if you look above the area in the level yellow arrow in the intima, those bright scattering, yellow scattering areas are cholesterol clefts and calcium. And so they lead to high scattering, which leads to a phenomenon known as multiple scattering, which isn't critical for the discussion, but it makes the border diffuse. And if we look on the right, there's not a lot of scattering in the intima, so the border is sharp. The image hasn't been distorted by scattering from the intima. And it's funny because I like the right side of this image where the black arrow is. So there's a diffuse border here, and it's just the intimal medial border. But the scattering in the intima itself is high, giving you a diffuse border. So this type of criteria doesn't work. But if you look at plaques, you're interventionists, your clinicians, you're used to looking at things qualitatively on an image and picking it out. That's what we really need, and we need these studies. But what happened is, so finally, when it got whacked in my brain, they just needed to be done. I was I don't know if I was waiting for people to do it or what. So let's say around 2010, 2012, we had the capability of doing it. Go out and search for collaborators to get us to coronary arteries. The NIH started not funding in vitro work, including adjuvant techniques, and so they started to say, and I understand their point. We've been funding you for 20 years. Well, where's the morbidity and mortality data? Which I also was asking, as discussed in a previous talk. But now we have the opportunities, morbidity and mortality data. Hopefully will come out of these trials that are currently going on, and to come back and look at this point. And I am very grateful to the new investigators who are driving these clinical trials, and also to Abbott and St. Jude, who I have no relationship with. I was one of the 3 people who formed Light Lab, but I don't have any relationship with Abbott. But keep going, guys. Now, long cores. Long cores are likely very important to interventionalists. They are going to be important to the story of, based on our data, the story of acute coronary syndromes. And so and I'll get into this now. So if we look at first an example plaque, the bottom is um, the pathology. The plaque is the artery's open, and the yellow is um, a long necrotic core, 40 millimeters long, that comes to the surface in intermittent points. It goes from the LAD, or the left main, all the way down the LAD. And this thing is not in one axial plane. So you know at the bottom of an OCT image, you see the longitudinal section, which I'll show in the next slide. But if you look in one axial plane, these things spiral. So it's not going to give you the true length. You have to look at it in more axial planes. You actually have to follow it. And that twisting can be seen in A, B, and C. You can see that it's toward the left of the artery, and this is an opened artery, and moves toward the right as it goes to C. So in order to know core length and areas where the core is close to the surface, we're going to have to pay attention to the length of these long necrotic cores. Now this really came to our attention, so we weren't the bright. I've been studying plaque mechanisms of coronary artery disease since the late 1980s, when I was a medical student, and the concept of looking at plaques longitudinally didn't manage to come to me. I was within the cross-sectional view that everybody else was, except for an accidental finding. It happened, and there's a long story behind why it was accidental, but I was looking at a case at Geisinger Hospital with Kishore Hajar, where they placed a stent, and downstream, 5 millimeters downstream, a clot formed. And they asked me what happened, and I'm going to go into the video. I'm not going to go through the individual OCT images. These can be found in the paper. But if we look at the video, so actually I want to pause this video for 1 second. So what just ruptured on the bottom was a TCFA. But there's also a TCFA on the distal. You can see it if you look closely at the picture. And this was on the OCT images. That was not associated with a long necrotic core. This TCFA was. So when the TCFA was ruptured by the stent, it blew out a core greater than 6 millimeters long and evacuated it. Now, so this can happen, and this time, in spite of the anticoagulants and antiplatelets, it occluded the vessel, and so it was just a massive core evacuation. Now, this isn't the primary mechanism for ACS, and we go into that in other articles, but knowing you're dealing with a long necrotic core is likely very important. And the TCFA that ruptured downstream during the procedure, nothing happened to, because it wasn't associated with a long necrotic core. And again, these things spiral. They come to the surface, they drive deep, and it's going to likely turn out that this is important information when you're placing a stent. So I'm just going to mention these two papers. So in 2019, looking back at that 2014 data, but analyzing massive amounts of histopathology, why do long cores appear to lead to heart attacks when you have a plaque rupture with a long core versus a short core? Because it's not likely to be, in the majority of cases, the massive evacuation. Initially we thought composition. It turns out that it's the failed healing after the rupture that's almost high probability is the cause. And that failed healing, these long cores don't get angiogenesis to all the areas it needs to, so you have no cellularity. So when you have a rupture, the clot forms, and after a rupture, it takes days to weeks before you actually occlude the vessel in many cases. If cells get in there, like smooth muscle cells and endothelial cells, you contain the clot. But if your blood vessels don't reach that area, you end up having a vessel occlusion. So these are the adjuvant techniques, and I'm not going to discuss them right now. I'm going to deal with them in a separate video presentation, go through them. Some of them I think are critical as we move forward with OCT in the coronary artery. Others a lot less important, but I'll deal with those separately in the next talk. So thank you very much.